Good morning, everyone. Today we're going to do 6.1, which is perpendicular and angle bisectors. If you want to write the title of the chapter on your notes, this is chapter 6, and it's titled Relationships Within Triangles. Okay. So, remember from previous lessons that a perpendicular bisector of a line segment does two things. It is perpendicular to the segment, and it is perpendicular at the midpoint, which in other words means that it cuts the segment in half into two equal pieces. And you can see that represented with this diagram right here. We have the perpendicular bisector of AB is line CP. So that line is what we would say, or what we would call, the perpendicular bisector, because it's cutting segment AB in half into two equal pieces, and it cuts it in such a way that it forms 90-degree angles. Okay, so the formal theorem is written right here, where it says if line CP is the perpendicular bisector of segment AB, then we know that AC, this segment right here, is congruent or equal to segment CB, okay? So in a plane, if a point lies on the perpendicular bisector of a segment, then it is equidistant from the endpoints of the segment. So if this point C lies on the perpendicular bisector, which is line CP, then we know that CA is equal to CB. The converse of this theorem, again, that's just when you're flipping the hypothesis and the conclusion. So in this case, we're given that segment DA is equal to segment DB, which then means that point D lies on the perpendicular bisector of segment AB. So in other words, if we're given that this is equal to this, then we know that this line is the perpendicular bisector of this line. Okay, so the two theorems are basically saying the same thing. The order is just reversed, so it's basically what information you're given. In this case, you're given that this is the perpendicular bisector, and you're allowed to make the conclusion that these segments are equal. In the converse, you're given that these two segments are equal, which then means that this line has to be the perpendicular bisector. To be honest, it doesn't change too much in terms of solving problems, but we'll get to that when we see an actual example. All right, so here we want to prove that segment CA is equal to segment CB, and we're given that CP, line CP, is the perpendicular bisector of AB. So as we always do, we're just going to set up our statement, reason, proof, and what we're going to do is prove that the two triangles are congruent. And then if we can prove that the two triangles are congruent, we could just use corresponding parts of congruent triangles to prove this final statement. So as always, we'll begin with the given, which is that line CP is the perpendicular bisector of AB, segment AB. That information is given. Now remember, that means we know two pieces of information. We know that CP is cutting segment AB in half, which means AP is equal, or we could say congruent, to BP. And the other thing that we know is that the way it intersects with segment AB forms 90-degree angles. So that means that angle CPB is congruent to angle CPA. And both of these statements here are by definition of perpendicular bisector. So just going to put the quotations to basically say copy paste that in, that reasoning. Okay, so currently what I have is a pair of congruent sides, a pair of congruent angles. So I just need one more information, one more piece. And the last piece is going to be that CP is congruent to CP by reflexive property of equality. Okay, now I have enough information to say that the two triangles are congruent. And the reason why they're congruent at this point is, I forgot the C, is by side, angle, side. If the two triangles are congruent, I know that CA is congruent to CB by CPCTC. And lastly, CA is congruent to CB by definition of congruence. Okay, very good. All right, now let's actually see some problems where we have to use the perpendicular bisector theorem or the converse. All right, here it says, is there enough information in the diagram to conclude that point N lies on the perpendicular bisector of segment KM? So can we say that this line here is the perpendicular bisector of this line here? Now remember, there's two things that we would need. We would need to know that this line here is cutting segment KM in half, which we can see that because these are tick marks, even though I know it's kind of hard to see. So we do know one piece of information, which is that KL is equal to ML, which means that the segment is getting cut in half. However, the second piece of information we don't know. We don't know if KM is perpendicular to LN, so we don't have enough information. Okay, we don't know if KM is perpendicular to LN, so we can't say that. And really, it's in the name. We have the bisector part because it's being cut in half. We don't have the perpendicular part, so we can't say that. All right. For these examples, not only are we going to find the value of the segment that they're asking us to, but we're also going to state what theorem we're using. So here we want to find the measure of RS, so find the measure of this side. Okay, now the information that we're given, that we're provided, is that this is equal to this. Sorry, I should highlight this, is equal to this. And that we have a 90-degree angle here. So what that means, what we're allowed to conclude is that SQ, line SQ, is the perpendicular bisector of RP. So by the perpendicular bisector theorem, if we know that this segment here is 6.8 units, then this segment here has to be 6.8 units as well. So by the perpendicular bisector theorem, we would say RS is equal to 6.8 units. Okay? All right. Next one. We want to find EG. Now, what information are we given? We do know that this is a 90-degree angle, but we don't know if this is equal to this yet. What we do know is that this segment is congruent to this segment, okay? So, because point H is equidistant from segment EG, we know by the converse of the perpendicular bisector theorem that EG is equal to 2 times 9.5, or we could say 9.5 plus 9.5, because if this is 9.5, this also has to be 9.5 by the converse of the perpendicular bisector theorem, okay? So what that means is that EG is 19 units long, okay? All right, another one. Here again, we are given that these two segments are congruent, and we're given that this is a 90-degree angle. So by the perpendicular bisector theorem, we know that CD has to be equal to AD, and I can use the expressions and plug in 3x plus 14 equals 5x, and then solve for x so that I can figure out what AD is equal to. So subtract by 3x on both sides, divide by 2, and I get x equals 7. Doesn't matter which one I plug into since they're equal, so I'm going to plug into this one since it's easier. AD is equal to 5 times 7, which is 35 units. Okay, so that was a perpendicular bisector theorem. The angle bisector theorem is very similar, okay? So in the angle bisector theorem, there is just an angle that is cut into two equal pieces, two congruent and adjacent pieces. So in this diagram here, AD is the angle bisector because it cuts this big angle, BAC, into two equal pieces, okay? Now, with the angle bisector theorem, if this is the case, if you have an angle that's being cut in half, then you know that the point on the angle bisector, so in this case D, is going to be equidistant to this ray and equidistant to this ray. So this is equal to this. BD is congruent to DC. That's the just regular angle bisector theorem. If you notice the converse, this is the information that we're given. BD is equal to DC. And so what we're allowed to conclude is that this angle and this angle are congruent, which means that AD is the angle bisector of BAC, okay? It's all about what information is given to you, whether or not you're using the regular theorem or the converse. Now, one other thing that I do want to point out is that when we talk about being equidistant, remember the distance from this point D to the rays, there could be a whole bunch. I could draw this line, I could draw this line, I could draw this line. The one that's considered the distance, the real distance, is the one that forms a 90-degree angle with the ray, okay? So let's look at these examples. We want to find the measure. This is referring to A, this is referring to B. For A, we want to find the measure of angle GFJ. So GFJ here. Oh, just kidding. We want to find the measure of GFJ. Now again, I'm going to have you guys state what theorem you're using. Based on the information in the diagram, I know that this is congruent to this. So I could have just used one tick mark, but it doesn't really matter. So by the converse of the angle bisector theorem, because those two segments are congruent, what do I know? I know that FJ, ray FJ, is the angle bisector of angle GFH, which means the measure of angle GFJ is equal to the measure of angle HFJ, which means GFJ is equal to 42 degrees. Because these two angles are congruent. Okay, looking at B. In this case, notice the information I'm given is that those two angles are congruent. So in this case, by the angle bisector theorem, I know that PS is equal to RS. So again, I can just plug in those two expressions and solve for x. And I get x equals 5, which if I want to find RS, I could plug it into either of those two expressions. So I'll just do the easier one, which is this one. So RS is equal to 5 times 5, which is just 25 units. Okay, last one. Write an equation of the perpendicular bisector of the segment with endpoints P at -2, 3 and Q at 4, 1. Now here there's two things that we want to do. Okay, so let's break it down into steps. Sorry, not two, three things that we want to do. We want to write an equation of the perpendicular bisector. Now, for writing an equation of, in this case, it'll be a line because perpendicular bisector is a line. If we want to write an equation of a line, then we have a couple options. We could do slope-intercept form, we could do standard form. In this case, we're going to do point-slope form. Okay, this is going to be the third step. We're going to do point-slope form, which if you guys remember, that's y minus y1 equals m times x minus x1, which means I'm going to need a point to plug in for y1 and x1, and I'm also going to need the slope to plug in. Okay, so here come the other steps. If I want the equation of the line of the perpendicular bisector, then perpendicular means when we're doing lines, I need a opposite reciprocal, actually let me write it underneath, opposite reciprocal slope in order to get perpendicular lines. So if I have a slope of 1/2, that's going to become -2. If I have a slope of 2/7, that's going to become -7/2, and so on. That's the idea there. Then that should actually be step 1, although it doesn't really matter, to be honest, which of these next two you do first. Then bisector meaning cut in half. So when we're doing when we're trying to cut something in half on the coordinate plane, what you want to do is the midpoint. So this is going to be step 2. You want to find the midpoint of the 2 points. The formula for that would be x1 plus x2 divided by 2, y1 plus y2 divided by 2. And again, midpoint because you're trying to cut it in half, and the midpoint is going to be right at the halfway point. So let's do it with these points. Step 1 is to find the opposite reciprocal slope, which means I need to find the slope of these 2 points. If we wanted to write the formula, that's y2 minus y1 over x2 minus x1. So that's going to be 3 minus 1 over -2 minus 4. So that would give us 2 over -6, or -1/3. But because I don't want the slope that connects these 2 points, but I want the slope of the line that's perpendicular to it, I'm going to take the opposite reciprocal of that -1/3. And so what I'm going to use is +3. And I'll show you what all this looks like on Desmo so you can get a visual of how it works. Okay, so that's step 1. Step 2 is to find the midpoint. So again, I have the formula here. I'm just going to do the sum of my x values divided by 2 and the sum of my y values divided by 2. So that's going to be 2 over 2, which is just 1, and 4 divided by 2, which is just 2. So the midpoint is 1, 2. Okay, now last step. I am going to take step 1 and 2 and use it to write the equation of the line. So y minus y1 equals m times x minus x1. So this is what I'm plugging in for m. And this is what I'm plugging in for y1 and x1. So that's going to be y minus 2 equals x minus 1. And then we want to simplify this to put it in slope-intercept form. And so this is your final answer, okay? Because it wants the equation of the perpendicular bisector, and that's what that is, okay? But it required us to do all the previous steps. Now, very quickly, let's just look at what we did. We used GeoGebra. Okay, so first, we have our 2 points, which are -2, 3, and -2, 3, and 4, 1. Okay, those are your 2 points. Now I want to draw a segment that connects them. Now remember, we want to write an equation of the perpendicular bisector of the segment with these endpoints, okay? So I know it's not A and B, it's P and Q, but it doesn't matter. We could change it if we wanted to, but I don't think it's that important. Q. Okay. So I need to find the line that's going to have opposite reciprocal slope to this one, which if you were to count the boxes, you could see what the slope is. Actually, it'll tell us. Okay, so that has a slope of -0.3 repeating, which is -1/3. And then I need to find the midpoint, which we already did. The midpoint was, I don't remember what it was. It was 1/2. Sorry, 1, 2, not 1/2. Okay, so that's the midpoint, which means, where is it? Okay, distance or length, that this to this is 3.6, and this to this is 3.6, so exactly like we said, it cuts it in half. And then if I write the equation of the line, y equals 3x, what was it, plus or -1? I think it was -1. Notice, I mean, it looks like they're perpendicular, but remember, we can assume. But luckily, I can check. I think this will tell me. No. There you go, 90 degrees. Okay, so we just constructed the perpendicular bisector that cuts segment PQ in half and creates 90-degree angles. Okay, and that's the end of the lesson.